Hi, and welcome to Online Assessment 4. In this assessment, we're going to be doing a few different things with one linear program, and this is to help us differentiate between the three kinds of linear programs we now know for a given one. Okay, so remember we have the original, which we also call the primal when we're thinking about the dual. We can take the dual of the LP. We can construct a canonical form. And from that canonical form, we, in general, need to construct the phase one. These are all different linear programs. Okay. So in this assessment, by the end of it, I'm hopeful that you're going to see all the different forms. Okay. In later assessments, we're also going to talk about, we're going to review what each of these does, but you've already seen what the canonical form of the phase one does. And in the next lecture, you're going to see also the duality theorems, which formalizes the power of the dual. Anyway, let's first take these forms. So we're going to first work on taking the dual of this example. So we're going to construct the dual. And I'm going to try to write down all the steps involved in that. So the first step is assign a dual variable for every constraint in the primal. So for every primal constraint. Okay. So here we have three constraints. And I'm going to call the dual variables U1, U2, and U3. I'll note this actually has 6 constraints, right? It has the 3 bound constraints. But when we talk about constraints for the purposes of the dual, as usual, we consider them in a different light than we do these bound constraints. We will be using these, but not for dual variables. These bound constraints, remember, are called this because they each constrain just a single variable to be greater or equal to 0 or less than or equal to 0. Okay, so those are the bound constraints. The second thing we do now is we form the Lagrangian, and this is the most important step in some sense because this is what lets us construct the dual linear program. The Lagrangian is formed by taking the objective of the primal and putting it on the left-hand side. And this next step, or this next part of this step, is really the most important one. You have to take the sense here and understand we want to bound this. It's a minimize. And because it's a minimize, we want a lower bound on a min. If this is a max, we would want an upper bound. Okay? And that really changes the sense of everything that follows this. Because for a lower bound, we want this to be true for any feasible solution. This has to be greater or equal to what comes next. Okay, so what comes next? Well, what comes next is going to be the dual variables multiplied by each of these left-hand sides added up. So it'll be the first left-hand side is U1 times x1 plus x2 plus x3 plus x4 plus u2 times the second left-hand side, which is minus 4x2 plus 8x4 plus the third left-hand side, which is u3 times x1 plus 6x2 minus x3. Okay. again, I'm going to want this to, now I'm going to just transform this to an equivalent thing where I collect the primal variables, each primal variable multiplied by what will become a dual constraint. And of course it has to be the same, so this is going to be equals to, and this equals to, let me just, so nobody's confused here, let me just write this. So this equal sign is clearly a part on its own. Okay, so it's not touching. It's still close, too close. I'll just be very clear. Okay, so I'm going to collect the primal variables. So first it's x1, and now the coefficients in front of x1, well, x1 is in the u1 equation. It's not in the u2, and it is in the u3. So it's just going to be, and it's just the coefficient there is 1 in both, so it's u1 plus u3. Okay. I'm going to write this bigger so I can be neater. Okay, so then the x2, well, the x2 has a u1, it has a u2, and a u3, so it'll be x plus x2 times u1, but the coefficient in the u2 equation is -4, so it's -4 u2, and in the u3 it's a 6, so it's +6 u3. There's an x3. Well, that's in the u1, not in the u2, but it is in the u3 with a -1. And so it's u1 minus u3. And finally, there's an x4. I know it's in the u1 with a 1, has an 8 in the u2, and is not in the u3. So it's +8. Okay. So there it is. And then finally, I still want this greater or equal to the right-hand sides multiplied by each of the dual variables. So that's 19u1 minus 55u2 plus 7u3. Okay, and that's just from the right-hand sides above. Okay. Those are always the coefficients of the dual variables. All right, so now I can start to look at this Lagrangian and use it to help me deduce the bounds on the dual variables and the constraints on the dual variables. Let's do the bounds first. So now, first, I'm going to do in step 3, I'm going to determine the dual bounds. And the idea here is that this Lagrangian inequalities, right, this greater or equal to over here, and this greater or equal to over here need to be maintained. And I wrote out this inner step, this inner equality, because it helps us understand how the bounds and then the constraints, which will be step 4, are constrained. First, let's do the bounds. The bounds are actually looking at, and I'll put this in red, this piece and this piece, okay? Because what we do is we say, all right, I need to maintain this inequality. I need to maintain this greater or equal to. And I'm multiplying u1 by this left-hand side, x1 plus x2 plus x3 plus x4, and I need that to be greater or equal to 19u1. And so the first thing I should say is the original form of this constraint was an equality. And I think, okay, well, for that equality to translate into a greater or equal to, do I need to do anything to u1 with the sign? Do I need to constrain it so the u1 can't be negative or the u1 can't be positive? And when I think about it, the answer is no. Equality constraints, well, they're very strict. That's going to be that satisfies the greater or equal to whether or not u1 is negative or positive. So here, u1 is allowed to be free. Okay, that's nice. Now I go to the next the next constraint here. It's the u2 multiplied by the minus on each side of this minus 4x2 plus 8x4 less than or equal to negative 55. Well, that's going the wrong direction. So if that's if the u2 is positive, this is going to be less than or equal to. That's not the correct form. So the u2 cannot be positive. So I have to make sure that it's less than or equal to 0. Finally, the u3 is being multiplied on each side. It's multiplying on each side of this greater or equal to constraint. Well, that's going the exact right direction. The only thing is I can't let it be negative, otherwise it'll shift the direction. So u3 has to be greater or equal to 0. Okay, so that's how we got the bounds. Note that the minimization is what made this a greater or equal to. And that's why we have the signs we have for the inequalities. Further, note that the equality constraints, you should be happy when seeing an equality constraint and you're constructing bounds because you know the dual variable will be free in either case. In some sense, that's you get that for free. Pun unintended. Okay, so now how do we construct the constraints? The constraints come from the bounds on the dual variables and then the coefficients for the, the bounds on the primal variables and the coefficients in the primal objective, so the original objective. In particular, we need that 5 is greater or equal to u1 plus u3. Of course, for this greater or equal to work, right, I'll put this in green. So here's the 5, here's the u1 plus u3. So here I'm going to write down u1 plus u3. And I want this to be greater or equal to 5. Really, I want x1 times that to be greater or equal to 5. And I see that x1 is free. Well, I have to be very restrictive on this. This has to be equal to 5. Because for this to be greater or equal to, if x1 is free, x1 can be negative or positive, which means that that inequality, the greater or equal to, is only true if I keep u1 plus u3 equal to 5. It's the only way, right? Because x1 could be negative. So if I made it greater or equal to 5, then that would mean that x1 if x1 were positive, that wouldn't work. And if I made it less than or equal to 5, that means that x1 negative wouldn't work. So because x1 is free, it has to be an equality constraint. Okay, let's do this here. The coefficient in front of x2 is a 1. And x2 is greater or equal to 0. So this has to be less than or equal to 1, right? For the u1 minus 4u2 plus 6u3 has to be less than or equal to 1 because I know x2 is never going to be negative because x2 is greater or equal to 0. That means that this less than or equal to is just going to sort of remain the same. Remember, we're going backwards. Like the objective is greater or equal to these right-hand sides, so these right-hand sides are less than or equal to the objective. Okay, we have x3 is greater or equal to 0. So actually, I already did the rationale here. We know u1 minus u3. This is going to be less than or equal to minus 4. And you might say, well, there's no x4 in that objective. Well, that's the same thing as a 0 coefficient. And x4 is less than or equal to 0. So this u1 plus 8u3, turns out this has to be greater or equal to 0. And the reason why is because we know x4 is going to change this direction of this less than or equal to a greater or equal to. Remember, I'm going from here and looking backwards to here. Okay, so this is, in some sense, I keep saying less than or equal to. It's because this right-hand side is less than or equal to the left-hand side. Okay, don't be confused by that. I can now, so this was step 4. I was determining the dual constraints. And then 5 is write objective in bounds. So the objective, remember, is this over here. Let's change this color to a light blue. The objective is here, so I write that over here. Because I was minimizing, now I'm maximizing. I want the best lower bound possible. So it's 19u1 minus 55u2 plus 7u3. And I write down the bounds that I had. I don't need to write anything for u1 because it's free. So I write u2 as